Good afternoon. Our today's topic is MOSFET and its analysis. We will wait for 1 to 2 minutes for other students and then we will start our class. In previous session, uh, up to that time, we will revise our previous session. In previous session, we have studied about the MOSFET. Then we have seen operation of N-channel, P-channel MOSFET. Then we have seen DC and AC analysis. In DC analysis, what we are doing? We are not considering the capacitor and we are कंसिडरिंग ओनली अ डीसी सर्किट और जो भी एसी सप्लाई है कैपेसिटर है हम उसको क्या कर रहे हैं एज अ ओपन सर्किट वी आर कंसिडरिंग देन वी हैव सीन एसी एनालिसिस हमने स्मॉल सिग्नल मॉडल एम्पलीफायर वी हैव सीन दिस then we have seen about the non-ideal effects which are occurred in a MOSFET analysis. These effects are occurring just because of there is a change in threshold voltage or sometime if we are applying drain to source voltage and it will be greater as compared to the VDS saturation. Then there some back effect, body effect, these effects are occurring and these effects we are calling as a non-ideal. Ideally, we are saying in saturation region, the value of ID current is constant, but practically the value of ID current is not constant. It will changes with respect to VGS and VDS. उसकी वजह से हमें क्या हो रहा है डिफरेंट फाइनाइट आउटपुट रेजिस्टेंस बॉडी इफेक्ट देन we have seen the temperature effect. These effects are calling as a non-ideal. So today we will see MOSFET and its analysis. MOSFET is also called as an insulated gate field effect transistor. This device called as IGFET. Why? Because current flowing through it can be controlled by applying electric field. We are calling this device as a voltage control device because its output current is controlled by applying electric field or applying voltage. हम क्या कर रहे हैं यहाँ का जो आउटपुट करंट है वो इनपुट वोल्टेज से कंट्रोल कर रहे हैं दैट्स व्हाई वी आर कॉलिंग MOSFET एज अ insulated gate field effect transistor. It is a voltage control device. You guys can see here these are the input characteristics ID current with respect to the input gate to source voltage. On x-axis there is a gate to source voltage and this is the output characteristics graph for the N-channel MOSFET. Here on y-axis there is a ID current. This is nothing but the output current. And on x-axis output voltage. This is nothing but the drain to source voltage. This characteristics is called as input and this is the output characteristics. If you compare MOSFET with BJT, BJT is a current control device, but MOSFET is a voltage control device because here output current is controlled by applying input voltage. It means what? हम input voltage को control करके output voltage control कर रहे हैं. If you compare again MOSFET with BJT, then you can see input impedance of MOSFET is higher as compared to the BJT. Then the size, if you compare in terms of size MOSFET with BJT, then you can see the size of MOSFET is smaller as compared to the BJT. That's why we are preferring MOSFET. So we can build number of transistor on a integrated circuit क्योंकि इसका जो size है वो कम है. Azhar, please mute yourself. Okay. Then if you compare MOSFET with FET, then you can see we can operate MOSFET as an amplifier. When if MOSFET is operating in saturation region. But in BJT, if BJT is working in a active region, then we can use BJT as a amplifier. These are the basic differences between the BJT and MOSFETs. If you see, there are two types of FETs. These are nothing but JFET and a MOSFET. If you compare JFET with MOSFET, then you can see JFET is working only in depletion region, but MOSFET is working in depletion as well as in enhancement region. So what does mean by depletion and enhancement region? If channel is permanently present, then we are calling this region as a depletion region. And if channel is not permanently present, we have to induce the channel by applying input gate to source voltage. Then we can call this FET as a enhancement. हम कब बोल रहे हैं उसको? जब उसमें चैनल इंड्यूस नहीं है एंड वी हैव टू क्रिएट. सो मॉसफेट चैनल नहीं है या फिर चैनल है तो भी वर्क कर रहा है. That's why we are preferring MOSFET, and in our syllabus we have to see enhancement MOSFET. If you compare again MOSFET with JFET in terms of input impedance, then you can see the input impedance of MOSFET is higher, very high as compared to the input impedance of a JFET. Then MOSFET is easier to fabricate as compared to the JFET. That's why we are preferring enhancement channel MOSFET. हमें हमारे सिलेबस में enhancement channel N channel और P channel MOSFET के लिए उसका operations, then उसके non-ideal effects we have to see. So we will see here the operation of transistors. If we are not applying any VGS, this is nothing but here they have written VSG. But if you guys see, positive terminal is connected with gate and negative terminal is grounded. So this is nothing but the VGS. But ये नीचे लिखने की जगह ऊपर लिखा है. That's why here they have written VSG. So if we are not applying any input voltage, it means what? If we are not giving any VGS, then channel will not get induced. Channel will not get induced. And here if you guys can see, here is an insulator which is coming between the channel and the gate. That's why here current will not flow. It means what? If we are not giving any biasing voltage to the gate terminal, two back-to-back diode exist in series, and this back-to-back diode will prevent conduction of current from drain to source. ये यहाँ पे क्या हो जाएगा? This back-to-back diode will prevent the conduction of current from drain to source, and no amount of current will flow. So this, if we are not giving any VGS, then we are getting here no value of current, and that region is called as a cut-off region. ये 0.1 का ये जो जितना region है voltage का, we are calling this region as a cut-off region, because here we are not getting any value of a output current. If you apply VGS and that value will be greater than 0, then there is a linear current will flow with respect to VGS. You guys can see here the graphical structure. Here you can see output ID current is flowing with increase in VSG, and it is increasing linearly. That's why we can call this region as a triode region, or you can call this region as a linear region or ohmic region. ये रीजन को हम linear region, ohmic region और triode region बोल सकते हैं, because here we are applying VGS and its value is greater than threshold voltage. That time what will happen? Here channel will get induced, and as channel will get induced, therefore there is a decrease in height of channel. Therefore there is a decrease in resistance of channel, and there is increase in depletion region, due to which we will get here increase in output current. हमें क्या हो रहा है यहाँ पे, जैसे जैसे हम VGS अप्लाई कर रहे हैं और वो भी थ्रेशोल्ड वोल्टेज से ज़्यादा, वैसे वैसे हमें क्या होगा यहाँ पे करंट जो है लीनियरली इंक्रीमेंट मिलेगा, क्योंकि डिप्लीशन रीजन बढ़ रहा है, रेजिस्टेंस ऑफ दैट चैनल विल बिकम less. It is nothing but you can call it is a negligible, and height of channel will become reduced. So we are getting here increase in ID current, and that is linear with respect to voltage. If you again apply VGS with small value of VDS, and if VDS becomes greater, then you can see ID current is increases. ID current is increases with value of VDS also. But if value of applied drain to source voltage is becoming VGS minus VDS equal to threshold voltage, then value of current remains constant. This region is called as pinch off of channel, or we can call this region as a saturation region. यहाँ पे क्या हो रहा है, जैसे जैसे तुम VDS का वैल्यू बढ़ा रहे हो और इतना बढ़ा रहे हो कि VGS माइनस VDS का वैल्यू जो है एग्जैक्ट थ्रेशोल्ड वोल्टेज के उतना बन रहा है, दैट टाइम क्या हो रहा है हमें, we will get here reverse biasing of a diode on channel side, and height of channel will become zero, due to which here we can call this region as a pinching off of a channel. And here we are getting the constant value of current, so we can call this region as a saturation region. If you see the equations of the N channel and P channel MOSFET, how we are getting these equations? If you are sorry, if you are deriving the circuit diagram for a MOSFET, and if you make hybrid model, then you will get, if we are not applying any VGS, then we are getting value of IDS as a 0 volt, and if you are applying value of gate to source voltage, and that value is greater than threshold voltage, but VDS is smaller or equal to than VGS minus VTH. At that time we are getting the standard formula of drain to source current. This is nothing but the output current, and here if you see, VTH is nothing but threshold voltage, VGS is nothing but gate to source voltage. If you see about the COX, this is nothing but oxide capacitance. If you see about the WL, it is a channel width. L is nothing but it is a channel length. Lambda is nothing but it is the channel length parameter. Channel length parameter. And if you calculate this mu n COX, this is nothing but the Kn, and it is the modulation parameter which we are using to derive the value of drain current. So this is the channel length parameter. And if you increase the value of VDS, and if VDS is becoming greater than VGS minus VTH, then we are getting constant value of current, and this current is called as a saturation current. This is the mathematical formula. I am providing you PDF on classroom for these equations, how we are getting this equation. Please go through this PDF. I will send it by today itself. Then we will see about the P-channel MOSFET equation. If we are talking about the P-channel enhancement MOSFET, then instead of VGS, we have to give minus VGS, or we can call this is the VSG. So if we are not giving any VSG, then we will get ID current will be 0. And if you give value, small value of VSG, and that is greater than threshold voltage, then you will get this value of ID current. If you are applying value of VSG and with VDS also, VSD. And if the value of source to drain voltage is becoming greater than VSD minus VTH, then we will get saturation current, saturation drain current, output current. That's why we can call it is the saturation output current. So we can derive these equations by using the hybrid model for the P-channel enhancement MOSFET. Here W is nothing but channel length, channel width, L is nothing but channel length. If you see about the COX, it is the gate oxide capacitance per unit area. If you see about the mu n or mu p, in n channel we will get here mu n. और यहाँ पे यदि p channel के लिए देखोगे, you will write here mu p, and it is the average carrier mobility. This is used to store the charge carrier. So these are the mathematical formula we are getting in cutoff, linear region and the saturation region for the ID current, and these are depending on the value of VGS and the VDS. Now we will see about the pinch off region. We are getting pinch off region in which region? Can anyone tell me? We are getting three regions in the output characteristics: cutoff, linear and the saturation region. तो हमें pinch off region कहाँ मिल रहा है, कोई मुझे बता सकता है? Please, anyone? So I will get you guys are hearing or not? Answer the question. Where we will get the pinch off region? We have seen three regions in the output characteristics. So pinch off region कहाँ मिल रहा है हमें? कहाँ हाइट ऑफ चैनल 0 बन रहा है? यहाँ मैंने सब कुछ लिखा है, वेयर वी आर गेटिंग. यू गाइज कैन सी हियर. माय स्क्रीन इज विजिबल?
यस मैम.
हाँ, तो कहाँ मिल रहा है पिंच ऑफ रीजन? कट ऑफ रीजन में मिल रहा है. We will get pinch off region in a saturation region, because when we apply VDS, you can mute yourself, Pranali. We will get pinch off region in a saturation region, because if you apply VDS and the value of VDS will reaches to VGS minus VTH, at that time what will happen? Inversion is disabled at the drain. If you see गेट साइड में जो है और ड्रेन साइड में है, यहाँ पे हम जब तक VDS का वैल्यू बढ़ा नहीं रहे हैं, जब तक हम VGS थ्रेशोल्ड वोल्टेज से ज़्यादा दे रहे हैं और स्मॉल VDS दे रहे हैं, तो हमें क्या मिल रहा है? यहाँ पे दोनों साइड में, गेट और ड्रेन के साइड में हमें क्या मिल रहा है? यहाँ पे इन्वर्जन मिल रहा है. बट इफ यू अप्लाई द वैल्यू ऑफ VDS and it reaches to VDS equal to VGS minus VTH, then inversion will get disappeared at the side of drain, due to which height of channel becoming 0, and just because of this region charges still flow, just that you can't draw higher amount of current with drain bias. That's why value of current will saturate, क्योंकि यहाँ पे क्या हो रहा है? हाइट ऑफ चैनल कम हो रहा है, और उसके साथ क्या हो रहा है? यहाँ पे वेन VDS का वैल्यू VGS माइनस VTH से ज़्यादा हो रहा है, दैट टाइम इन्वर्जन विल गेट डिसेबल्ड at the side of drain, due to which here we will get disabled inversion only at the source terminal. हमें सिर्फ सोर्स टर्मिनल के तरफ मिलेगा, बट हमें ड्रेन टर्मिनल के इन्वर्जन नहीं मिलेगा. दैट्स व्हाई वी कैन नॉट इंक्रीज अमाउंट ऑफ करंट. The value of current will be remains constant. You guys can see the structure here. ये यहाँ पे here we are getting the constant value of current. Ideally, practically थोड़ा change होता है, और due to this reason we are getting the non-ideal effect. But ideally what we are saying here, height of channel is becoming 0 and the inversion at the drain is becoming 0, due to which we are getting here constant value of id current, and if we are increasing vds further above the vgs minus vts, value of id current will not increase. Okay, these are the output characteristics, and we will get pinch off region in a saturation region. These are the ideal static ideal characteristics for the N channel enhancement MOSFET. If you guys see here, the vein value of VGS is smaller than threshold voltage. We are getting here ID current 0. This region is cutoff region. And when we are applying VGS becoming greater than threshold voltage, then we are getting value of ID current increases linearly. That's why we are calling this region as a linear region. And if value of VDS we are giving with small amount of VGS, and if value of VDS will reaches to VDS minus VGS will become threshold voltage, then we are getting constant value of current, and this region is called as a saturation region. These are the drain current equations. If you see for the linear equations, we are getting ID equal to the width of channel with respect to length of channel into Kn. Kn is nothing but it is parameter which is used in a modulation parameter which is used to calculate the value of ID current. If you calculate Kn parameter, you will get it is nothing but COX into mu n. Mu n is mobility, charge carrier mobility for N channel, and COX is the oxide capacitance. Then we will get the equations for the trans channel conductance and the transconductance. You will get these equations by using the hybrid model. As we know, conductance, transconductance is the reciprocal of the resistance, and according to Ohm's law, we are getting R equal to V by I. So transconductance क्या हो जाएगा? Opposite, ID upon VDS. And if you see about the transconductance for the input, then you will get it is the ID current with respect to input voltage. This is nothing but VGS. You can calculate these equations. These mathematical equations are useful to solve numericals. I will provide you the numericals, और मैं तुमको अभी जो असाइनमेंट मैंने जो आज भेजा है, तुमको 20 अक्टूबर तक असाइनमेंट सबमिट करना है, और उसमें भी दो न्यूमेरिकल्स है. You are supposed to solve these numericals. In saturation region, if you calculate the value of conductance and transconductance, then value of channel conductance you will get 0, because here if you see in saturation region we are getting value of current constant, so we are getting here channel conductance 0. If you calculate transconductance, you will get this is nothing but output current with respect to input current. We are taking derivative because we have to see the change in conductance. So we are taking here derivative. If you see the hybrid model which we are using to derive the equations for the GM, this is nothing but transconductance, or the ID, it is nothing but drain current. This is the equivalent AC circuit which we are using for the analysis of the MOSFET. This circuit is for the higher frequency. In lower frequency, what we are doing? We are not considering here capacitor, because in lower frequency, if you see, this is the gate looks like a open circuit, and source to drain output looks like a current source with ये drain to source का देखोगे तो you guys can see it is looking like a current source with channel conductance, and in higher frequencies it is looking like a closed circuit because we are using here capacitance. Input stage looks like a capacitance, gate to source voltage and gate to drain overlap. Output capacitance are ignored here. because the drain to source capacitance is having small value. These are the equations we are getting after solving this hybrid model for the equivalent MOSFET circuit for higher frequency. If you calculate the value of frequency, then we will get the frequency equal to Gm. This is nothing but transconductance with respect to 2 pi into gate capacitance. If you calculate in terms of channel length and channel width, in terms of charge carrier mobility, then we will convert Gm का जो इक्वेशन से मैंने क्या किया है वो omega by L or a Z by L. You can write anything for the width of channel. We can convert these equations and we will get the value of frequency here. This is the frequency we are getting here. And if it is a inverse transit time, then we are getting the value of omega is nothing but 1 upon L by V. V is nothing but voltage. And we can write here mu n Vd upon L. If you see the speed and power dissipation, we get here power dissipation because we are using here capacitor in the circuit, and we know capacitor, if we are using capacitor, it will take some value of potential difference which we are applying at the input. हम क्या कर रहे हैं, इनपुट में जो भी पावर अप्लाई कर रहे हैं वो क्या हो जाएगा, वहां उसमें हमको थोड़ा ड्रॉप मिलेगा. तो वी कैन से these capacitors will take some value of power. That's why we can see here the power dissipations. If the value of oxide capacitance is small, but if we are taking internal capacitance and the drain capacitance, मतलब source और drain capacitance यदि तुम ले रहे हो, then you can lose the control of channel potential. It means what? You can lose the control of channel, means you will lose the control of current, because if channel will change, height of channel will change, then value of ID current will change. That's why we can call this as a drain induced barrier lowering. If value of oxide capacitance will increase, you want to make sure you don't control the parasitics which do not contribute to the current. मतलब क्या, जब तुम capacitors use कर रहे हो, we know the value of output current is depending on channel, because we are using here enhancement MOSFET, and enhancement MOSFET channel is not permanently present. We have to create the channel. That's why if we are using here capacitor, then there is a change in channel barrier. That's why we can calling this as a channel induced barrier lowering. These are the dynamic power dissipation and the static power dissipations. We are getting these power dissipations in the MOSFET. If you see static power dissipations, then static power dissipations is called as leakage current, or we can call this current as a subthreshold current. And dynamic जो power dissipation है, we can call dynamic power dissipation as a short circuit power dissipation, or we can call changing and charging and discharging power dissipation. मतलब क्या हो रहा है, if you see about the static power dissipations, we will get static power dissipations when the circuit is in off condition. It means what? There is a leakage current and the subthreshold current. This leakage current will the flow from subthreshold gate oxide leakage and reverse bias diode. And if you see about the dynamic power dissipations, then we can calculate the value of dynamic power dissipation by using the short circuit. And if you make the short circuit, Then by changing and the charging and discharging of a capacitor, you can calculate the value of dynamic power dissipation. These are the mathematical formula we will get in power dissipation. If you compare BJT with MOSFET, then you can see it is a RTL logic with respect to BJT's CMOS logic. Then DC input impedance of a MOSFET is finite as compared to the BJT. मतलब क्या? If you compare BJT and just wait for a minute, इलेक्ट्रिसिटी गई है, मैं नेट कनेक्ट कर रही हूँ, just wait for a minute. Am I audible? Am I audible?
Yes, ma'am.
Okay. If you compare BJT with MOSFET, then you can see its input impedance is infinite. It means what? Its input impedance is higher as compared to the BJT. And MOSFET is a unipolar device, but BJT is a bipolar device. Here, current will flow just because of majority as well as minority carrier in a BJT, because ये जो है BJT bipolar है, but in MOSFET current will flow just because of the majority carrier. And as its input impedance is infinite, then here we will get output current will have many inputs. It means if you compare in terms of fan out for BJT and MOSFET, then you can see MOSFET's fan out is higher as compared to the BJT because its input impedance is high. Normally, BJT is having higher transconductors and current. So, these are the faster. But if you compare in terms of size, then size of MOSFET is smaller as compared to the BJT. It means what? MOSFET is compact size as compared to the BJT. BJT is current control device and MOSFET is a voltage control device. If you write the equations for the output current, as MOSFET are having three terminals, gate, drain and source, output current for N channel will be ID current जो ड्रेन से फ्लो हो रहा है. और बीजेटी में क्या है? थ्री टर्मिनल्स, इमीटर, बेस, कलेक्टर. सो IC will be collector current will be the output current. If you see the mathematical formula, there is a big difference in the equations for the output current for MOSFET and the BJT. And MOSFET size is compact. MOSFET is a voltage control device. That's why we are using MOSFET. Here current will flow just because of the majority carrier. Today's MOSFET is having drain current higher as compared to the collector current due to the ballistic operation. Actually क्या होता है, जो current और transconductance होता है बीजेटी का ज़्यादा था, बट टूडेज अभी जो नए नए निकल रहे हैं मॉस्फेट, इफ यू सी इट्स आईडी करंट इज हायर, मतलब आउटपुट करंट इज हायर as compared to the BJT. Just because of these reasons, we are preferring MOSFET instead of a BJT. Thank you. If anyone is facing any issue, then you can ask. I will take firstly attendance, then we will revise our today's class. Just wait for a minute. I am taking attendance. In today's session, we have seen about the MOSFET and its analysis. This is the input characteristics. This is the output characteristics. If you are drawing the pictorial graph of input current with respect to the gate source voltage, then we can call output current with respect to the input gate to source voltage, then we can call this as a input characteristics. And if you are drawing pictorial graph for the output ID current with respect to source to drain voltage, drain to source voltage for the N channel, then we can call this as a output characteristics. And if you are drawing for the P channel, तो P channel के लिए तुम क्या करोगे? ये VDS को VSD लिखोगे और ये जो VGS उसको VSG. Instead you can ड्रॉ ये फर्स्ट क्वाड्रेंट में ग्राफ किया है, उसकी जगह तुम थर्ड क्वाड्रेंट में, तीनों भी निगेटिव, दोनों भी निगेटिव, VSG एंड ID यू कैन ड्रॉ इन थर्ड क्वाड्रेंट। और वहां पे तुम VSG और ID नाम दे सकते हो, VSD और ID। और तुम यदि तुमको यही ग्राफ चाहिए तो तुम यहाँ पे चेंज करोगे, VGS की जगह यहाँ पे क्या करोगे, VSG, और VDS की जगह VSD। If we are not applying any input voltage to the gate to source terminal, then we are not getting any output current. We are calling this region as a cutoff region. If we are giving small amount of VGS and its value is greater than threshold voltage, then we are getting ID current which is increasing linearly. Or if we are not applying any VGS, or if VGS value is smaller than threshold, मतलब तुम दे रहे हो वैल्यू इनपुट वोल्टेज को बट उसका वैल्यू थ्रेशोल्ड वोल्टेज से कम है, तब भी हमें आउटपुट करंट जीरो ही मिलेगा। when value of input gate to source voltage will reaches to threshold voltage, at that time we will get increment in a output ID current, and this region we are calling as a linear region. And if you are increasing again value of VGS and we are giving VDS also, and the value of VDS will reaches to VDS, VGS minus VDS is becoming equal to or greater than threshold voltage, then we are getting constant value of ID current, and this region is called as a saturation region, or we can call here pinch of channel. These are the mathematical equations for the ID current. If there is a cutoff region, we are not getting any current, so IDS will be 0 ampere. And linear equation saturations, these are the mathematical equations. Mu is nothing but it is the charge carrier mobility. COX, it is the oxide capacitance. W, this is the width of channel. L is nothing but length of channel. VGS, VDS वो तो तुमको पता ही है. If value of VDS will reaches to VGS minus VDS will becoming threshold voltage, then we are getting constant value of ID current because the height of channel becoming 0. And here if you see about the drain and source structure, inversion region at the drain will becoming disabled, due to which we are calling this region as a pinch of channel, because here we cannot change the value of ID current. This is depending on a channel. That's why we are calling this region as a pinch of or current saturation region. This is the ideal characteristics. कट ऑफ रीजन लिनियर, जहाँ पे लिनियरली इंक्रीमेंट है और जहाँ पे करंट कांस्टेंट है, दिस इज द सैचुरेशन. These are the mathematical equations for the ID current with small value of VDS. And if you increase VDS, then we can call this is the saturation region. Here, these are the values for transconductance and the channel conductance. If you see, transconductance is the reciprocal of a resistance. So it is the ratio of change in current with change in voltage. This is the equivalent AC circuit to derive the value of drain current and to derive the value of transconductance. If you are increasing frequency, then we can see this circuit as a short circuit, because ये यहाँ पे यदि देखोगे तो वहाँ पे सोर्स और ड्रेन जो था, these are looking like a open source, but यहाँ पे है, यहाँ पे मैंने कैपेसिटर कनेक्ट किया है. If you see here, gate looks like a open circuit, but here gate looks like a short circuit when we are increasing the value of frequency.